All right, so we're going to start our discussions today on something called the discrete time Fourier transform. And so we're already familiar with the continuous time Fourier transform, the DTFT, which is the acronym we're going to use for discrete time Fourier transform, is just the Fourier transform which is applicable to discrete time signals, right? But there are some fundamental differences from the continuous time. And all of those differences actually stem from the fact that complex exponentials in discrete time are slightly different. I mean, there are some salient features of it, and especially with regards to the periodicity and the frequency variations that are different. And I'm just going to give you a quick review of those properties before I start talking about the DTFT, right? So the first thing is if I have a discrete time exponential, right, which has a frequency omega naught, and so the x of n is the form e raised by j omega naught n, and of course n here is an integer, right? So it could be any integer over the negative or positive, right? The first thing we found out was that there is a periodicity in the frequency, right? So the frequency omega naught is exactly the same as the frequency omega naught plus 2 pi, right? And any multiple of 2 pi onwards, right? So there was this inherent frequency periodicity in the frequency, because of which we concluded that it's enough for us to just consider omega naught um, in an interval which is of length 2 pi. In other words, ya to 0 to 2 pi, or another that we consider is from minus pi to pi, and both are equivalent, right? And what that's really saying is that if I had the frequency axis, right? So let's say if I had the frequency axis here, um, and this was omega, right? What that means is, as far as frequencies are concerned, the unique frequencies are only going to reside within an interval of length 2 pi, right? So all frequencies between 0 and 2 pi, these are the unique frequencies that are there for the discrete time case. And of course, the reason is because as soon as I move um, ahead of this interval, as soon as I step outside of this interval, for example, in the interval minus 2 pi to 0, I mean, for any frequency that I find here, for example, this is um, minus pi, right? The equivalent frequency is going to be plus pi here, because that's a 2 pi multiple displacement from minus pi. Okay, so minus pi and pi are going to be similar. Minus zero point 0.5 and 1.5 pi are going to be similar, and so on and so forth, right? So this is enough for us to just consider frequencies within 0 and 2 pi, or from minus pi to pi. Okay, that was the first fundamental difference between continuous time exponentials and discrete time exponentials. The second was that the highest frequency, because of this fact that the frequencies are periodic, the highest frequency that there exists in the discrete time case is pi, right? It's pi radians per sample, right? And that's the highest frequency that corresponds to an exponential, which is minus 1 raised to power n, as we talked about, which has a period of 2. That's the highest rate of oscillation that you can get for any discrete time signal, right? And as a consequence, when we say, Kiji, these frequencies here around 0 and 2 pi, so let me draw it again. So frequencies around 0 and the frequencies around 2 pi, these are the low frequencies. So this corresponds to the low frequency regime, right? And the region around pi is the high frequency regime, right? So this is where the high frequencies are. And as you go on increasing from pi, as you found out, pi said you start going towards 2 pi, the frequency actually starts decreasing, or the rate of oscillation starts decreasing, right? So that's another one of the important factors. Okay. Any questions about discrete time exponentials before I give you an overview of continuous time Fourier transform? Okay. Right. So here's a quick review of the continuous time Fourier transform. And we're going to try to draw parallels from there. Right, so Fourier analysis states that any continuous in the continuous time domain states that any continuous time signal can be represented as a superposition of scaled complex exponentials, right? And in other words, it said that the x of t can be written as that superposition. What that means is what that implies is the synthesis equation, right? So this minus infinity to plus infinity, and then is you had x of j omega and e raised to power j omega t times d omega, right? And this was the superposition, right? And where this x of j omega was called the Fourier transform and was computed by this analysis equation, and this is integral over time minus infinity to plus infinity x of t e raised to power minus sorry, this is omega j omega t times dt, and this was the analysis equation. Can somebody tell me, I mean, this what does a superposition expression imply, or the inverse Fourier transform relationship? What does it mean? So, or in other words, if I let's say, Chale, if I give you some Fourier transform, take it off some arbitrary signal, and let's say that Fourier transform looked something like this. Let's assume it's real, right? So it looks something like this. And the Fourier transform evaluated, let's say, at pi radians per second, this is pi, this pi radians per second is some value which is x of j pi. What does this value x of j pi indicate, or what does this represent? Ji Abdullah.
Sir, this represents the contribution of that frequency in the energy of the signal.
Good, excellent, right? So in other words, कि अगर मैं इस what it says is कि my signal x of t, which is a continuous time signal, is actually made up of an infinitely many complex exponentials of frequencies that vary from minus infinity to plus infinity. So the frequencies vary from minus infinity to plus infinity, right? And x of j omega, as omega changes, just indicates what the contribution for the corresponding complex exponential of that frequency is, right? So x of j pi, whatever this height is, that represents कि यार ये जो pi radians per second में घूमता हुआ एक exponential है, उसकी signal के अंदर क्या contribution है. And similarly, I could have said x of j 2 pi radians per second पे जो घूमता हुआ exponential है उसकी frequency में क्या contribution, and so on and so forth, right? So it's a contribution. It represents the contributions of different frequencies in the continuous time domain signal, right? And this contribution is found out by the forward Fourier transform, which is x of j omega equals x of t e to the minus j omega t. Okay. Now, a similar thing applies to the discrete time case as well. And the way we went about, remember, deriving the continuous time Fourier transform was by first looking at the Fourier series, right? And extending those ideas to aperiodic signals by taking t going to infinity and then seeing what does Fourier series translate to, right? And a similar thing also applies to Fourier discrete time Fourier transform as well, right? However, I mean, since we're short on time, we only have a few lectures left, right? So we are going to skip our discussions on discrete time Fourier series, right? So we're not going to go that route in deriving what DTFT is. We're not going to go the DTFS route, the Fourier series route, in deriving what DTFT is. Instead, I'm just going to try to draw parallels from the continuous time Fourier transform and just see what kind of ideas are going to be applicable in the discrete time case. I mean, what translates directly and what needs to be changed, right? So what the Fourier analysis in the discrete time case indicates is once again that any discrete time signal, whether that be periodic or aperiodic, can be represented as a superposition of discrete complex exponentials of varying frequencies, right? So any signal. So that therefore the complex exponentials are once again in the discrete time case as well, building blocks of signals, building blocks of time domain signals, discrete time domain signals, right? So so if I have the frequency axis and see, I want to see KR, but I want to see क्या different क्या चीज़ है, right? So let's say this was the omega axis, but I know in the frequency domain, the frequencies of the exponentials in the interval 0 to 2 pi are unique, but outside of this interval, as I 2 pi से थोड़ा सा मैं frequency increase करता हूँ, the frequency that I get is actually the same as the one that I had in the interval 0 to 2 pi, right? So the unique frequencies only reside between 0 and 2 pi. So the complex exponentials, which are of unique frequencies, those frequencies only reside between 0 and 2 pi, right? So as opposed to the continuous time domain, where the frequency contributions were actually from minus infinity radians per second to plus infinity radians per second, that cannot hold in the discrete time. Why can it not hold? Once again, because the frequencies, unique frequencies only reside between 0 and 2 pi radians per second. Okay, radians per sample. And the Fourier transform, Ji Hassan, you have a question?
सर, तो मैं ये पूछ रहा था कि अगर हम लोग फोरियर ट्रांसफॉर्म करते हैं
Yeah.
तो हमें क्या कहते हैं उसमें पीरियोडिक सिग्नल मिलना चाहिए, बिकॉज द कंट्रीब्यूशन लेट्स से जो पाई की होगी वो अगले 3 पाई की भी होगी, तो
All
वो भी
right.
हमें एक पीरियोडिक सिग्नल क्या नजर आना चाहिए, बिकॉज देयर कंट्रीब्यूशन शुड बी द सेम बिकॉज दे रिप्रेजेंट द सेम फ्रीक्वेंसी फॉर डिस्क्रीट सिग्नल.
So, if I understand you correctly, what you're saying is that because there's periodicity in the frequency domain, there should be periodicity in the time domain as well when I add them up. Is that what you're saying?
सर मैं इसलिए कह रहा हूँ क्योंकि हमारे जो यूनिक फ्रीक्वेंसीज इन दिस केस है वो 0 to 2 पाई है ना सिर्फ,
Yeah. Yeah.
तो उसके बाद जो भी हमें क्या कहते हैं फ्रीक्वेंसी पे कंट्रीब्यूशन नजर आनी चाहिए,
Yeah.
that should be equivalent to the same one, just minus 2 pi, yeah, some integer minus into minus 2 pi.
Yeah. That's true. Exactly. So, okay. Okay. So you're saying that DTFT periodic होना चाहिए.
जी जी जी.
Yeah. So excellent, right? So that's what we're going to find out in just in a bit, right? And that's once again because of the fact that these 0 to 2 pi value frequencies exactly वो हैं जो minus 2 pi to 0 है, right? So there's periodicity, and that's something we're going to see. Okay. Now, so I'm going to state some results here, and I say that can x of n once again be represented as a linear superposition of discrete time complex exponentials, and Fourier once again analyzed, yes, they can be, right? What form they can be? This form, more or less similar to what we had in the continuous time case. And you have x, which is a Fourier transform. I'm going to come to this notation, why we have this notation here, right? And you have e raised to power j omega n times d omega. Now, let's just look at this equation here and let this rest here for a while and try to absorb what this is really saying, or how is this different than the continuous time counterpart, right? Continuous time counterpart, let me write this here. This continuous time counterpart was x of t equals 1 upon 2 pi, right? And there was this integral from minus infinity to plus infinity. And what I had here was a function of omega, and then e raised by j omega t d omega. And you see the equation is very, very similar, right? And they're parallels that you can draw, right? You have the Fourier transform, which is this part here. And this was the continuous time Fourier transform, right? And this here, by extension, should be the discrete time Fourier transform, right? But how is it discrete? The reason why it's discrete, the left-hand side is discrete, is because this here is a discrete time exponential. Because n, why is it discrete time exponential? Because n is a part of the integer set, right? But this here is a continuous time exponential, right? So that's a fundamental difference, right? That's a fundamental difference. Hassan, do you still have a question, or was this from before?
Sorry sir, वो
All right.
पहले से था.
Okay. Right. So This x of n is called the synthesis in the discrete time case. It's called the synthesis Kelly, yeah, inverse Fourier transform. IEDTFT, right? Inverse discrete time Fourier transform, right? This equation here. Now, I have deliberately not put any limits in this integral here because I want you to take a guess. What should these limits be? Right? If I look at this expression, if this integral was from minus infinity to plus infinity, what this would have been saying is, yaar, what is the contribution of the frequencies of in discrete time exponentials as they range from minus infinity to plus infinity? But we don't have unique frequencies anymore in the discrete time, right? So therefore, this should go over a finite set. And as Talha and Hassan point out, they should go from 0 to 2 pi. And the reason is because the frequency contribution, as I've been saying all along, the unique frequencies are only between 0 and 2 pi. Now, can somebody say, tell me कि यार 0 to 2 pi होना चाहिए या कुछ और भी हो सकता है? If somebody comes in and says कि जी 0 to 2 pi is okay, right? But this could be something else as well. जी Talha.
So it can be minus 2 pi to 0, or it actually it has to be like an interval.
Excellent.
Pi.
It could be from minus 2 pi to 0, right? It could be from minus 2 pi to 0. It could be from pi to 3 pi, right? And as Abdullah points out, exactly right, Abdullah, this has to be, and Omar as well, Omar Abdul Jalil, right? So this has to be over an interval of 2 pi. And does not really matter where that interval is. That interval could be anywhere as long as it's over an interval or unique interval of length 2 pi, right? That's notation I'm going to use as the following. So I'm just going to write 2 pi at the bottom here. Just like what we did in the Fourier series, maybe we just wrote down the capital T at the bottom that just says kg, this integral is over any interval of length capital T. Just like this integral is over any interval of length 2 pi, right? So this is what it indicates. Well, let me write this in. This means integral over any length 2 pi, right? Now the question is, what is the Fourier transform relation? So this was the inverse Fourier transform. What about this x of e raised to power j omega? This x of e raised to power j omega is given as the summation, and you have to take my word for it here. I'm not going to spend time on the derivation here. This is this summation from minus infinity to plus infinity, x of n e raised to power minus j omega n, right? So this is called the discrete time Fourier transform. And let me just write this down again. X of n, whereas is 1 upon 2 pi, integral over 2 pi, x of e raised to power j omega, e raised to power j omega n times d omega. And this is the inverse discrete time Fourier transform, or the synthesis. And of course, this is the analysis, or the analysis. Okay.
Sir, आप मुझे step by step casting कैसे step by step?
What do you mean step by step?
Fourier transform step by step.
So Fourier transform, if you were to compute Fourier transform, right, of a discrete time signal x of n, right, you would use this forward Fourier transform relationship that you see on the screen, जो मैं highlight कर रहा हूँ, right? So you just take it up, multiplied by the signal e to the minus j omega n, right? And then sum from minus infinity to plus infinity.
जैसे जब भी मैं करता हूँ तो मुझे लंबा equation लिखनी पड़ती है, लंबी equation.
Yeah, so we will look at some examples and see how we can resolve this, right? But this is an infinite sum, right? And this may converge or this may diverge, right? As we're going to see. Okay? And then if you were to find the inverse Fourier transform, given a Fourier transform.
सर ये मतलब ये जो कन्वर्जन से कन्वर्जन के 0 पर चले जाएगी 0 पे क्योंकि e की पावर माइनस j तो भी होती है ना
So we
और n is going to
converge कब करता है कब नहीं करता, we're going to come to that in just a bit. Okay, so and if you were to find the inverse Fourier transform, this is what the relationship that you would use. Okay, all right.
okay.
And we're going to see some examples and hopefully competitions kaise karni hai, that should become clear. All right, now like I said, I want to say something about the notation here. I mean, this notation is I mean, cumbersome to say the least, and not at all clear. I mean, why does it have this e raised to power j omega inside of it? I mean, what's the purpose behind something like this, which is e raised to power j omega? Iska kya maqsad hai, right? And the answer to this follows similar reasoning as was the case for continuous time Fourier transform as well, right? वहां पे क्या था? वहां पे था कि you had a x of j omega. And why did you have a j omega? Can somebody point out to me why was it j omega? We had this discussion on our discussion forum. वो j omega क्यों है? Right. So perhaps right. So Umar, I'm asking about the continuous Fourier transform, right? So continuous Fourier transform. The reason why Oppenheim uses j omega in the continuous time Fourier transform is just to illustrate, make a connection with something called the Laplace transform, right? So that, and he says that the Laplace transform and continuous time Fourier transform are related. How? That the continuous time Fourier transform is nothing but the Laplace transform evaluated on the j omega axis. But at the end of the day, this x of j omega is a function of omega only. It's not a function of j. J is just a constant, right? It's only a function of omega, right? But that particular notation that he uses is just to build that bridge to Laplace transform later, right? Similarly, in the discrete time case, right? In the discrete time case, there's something called the Z transform, which we won't have time to study, right? And it turns out that the Fourier transform is a Z transform evaluated on e raised by j omega, which is a unit circle, right? So, I mean, forget about the details, but that's one of the reasons why Oppenheim uses this notation. Now, in principle, I should not have used this notation. Why? Because we're not going to study Z transform. We're not going to have time to study Z transform, right? So perhaps I should have just used this relationship, x of omega, right? And that makes things less confusing, right? But the reason why I did not follow this notation is because if you go through the textbook, I mean, the textbook uses e raised by j omega. Sare problems, sare examples, uski sari discussions are with this notation. And it's better for me to just introduce x of e raised by j omega so that you can make those connections when you're reading up the textbook, which you should, right? And when you're solving practice problems in the book, which you should, right? That's the reason why I'm using x of e raised by j omega. But for all intents and purposes, this is this function here is only a function of omega, right? It's not a function of e raised by j omega. It's a function of omega because that's the independent variable. Okay, Talha, you wanted to say something? Ji?
So I got it.
Okay. All right. So this is the Fourier transform, the inverse Fourier transform, right? Any questions about this before I solve some examples? Okay. Right. So this is the first example. And you have a discrete time signal, which is x of n, and just a simple signal a raised to power n u of n. right? And one of the conditions that is given to us that the absolute value of A is less than 1, right? And let's just also consider the fact that A is real. It does not have to be. I mean, for all the computation that we're going to do, A does not have to be real. But when we do the sketching, तब हम A assume करेंगे real है, right? So if x of n is A raised to power n u of n, what does this look like? So can somebody point out to me what does it look like? And if I were to sketch this out, कौन बताएगा? So what does this signal look like as a function of n? Q Hamza Rashid? If absolute value of A is less than 1. Okay, 0 before 0.
सर 0 1 के दरमियान होगी.
So this is A of n, U of n, right?
Yes. The question, जब हम करते हैं सर हमें ग्राफ के हिसाब से लगाए फिर से करते हैं वो क्या कहते हैं वैल्यूज मतलब कि माइनस इनफिनिटी को इनफिनिटी अगर कोई वैल्यूज हो के कोई क्या कहते हैं बाउंड्रीज हो तो बाउंड्रीज क्या कहते हैं हम कैसे लगाते हैं कहते हैं सिंथेसिस फंक्शन में कैसे लगाते हैं.
Yeah, but there are no boundaries here. I mean, so this signal extends infinitely towards all the way up to infinity, right?
Okay.
But it is 0 for all values of n, as Talha points out as well. Is 0 for all values of n, which are less than 0. ठीक है? और 0 पे क्या value है? The 0 पे ये 1 value है. Right? And then, as Abdullah says, it's an exponentially decaying function, right? And so this is going to be A here, and then this is A squared, and then A cubed, and this exponentially decays, right? And so on and so forth. So this is
Why sir? Why?
because this is A raised to power n, right? If A is less than 1,
Oh yes, ठीक है समझ आ गया. Thank you.
right? So, okay. Now, is this correct, or have I missed something? Is this correct, or have I missed something? I have missed something, yes. What have I missed something? Or this particular sketch is applicable for one particular case. For another particular case, this sketch should be something different. Can anybody? Right? This is for n is greater than 1, right? N is, Abdullah, what do you mean by that?
Oh, sorry, never mind.
So Talha, unmute करें बताएं.
That is just for if A is between 0 and 1.
Yeah.
Okay, modulus at
Excellent.
if A is between minus 1 and 0, तो हम उसको consider नहीं किया है.
Excellent, right? So this is only the case when A is between 0 and 1, right? But what happens if A is between?
Exponentially increasing.
फिर क्या होगा?
Exponentially increasing.
No, increasing तो नहीं होगा.
Alternate करेगा.
Alternate करेगा. Excellent. Right, so it's going to be 0 here, and then minus, and then plus, and then minus, and then plus. It's going to be an alternating signal, right? So this is -1, this is 0, this is 1, 2, 3, 4, right? So this is an alternating signal. The absolute value for this, of course, does decay exponentially. Okay? The absolute value for both of them are the same, right? लेकिन जो है, so if they're not the same, it depends कि A की क्या value है, right? So it plus minus plus minus plus minus. So that's how it's going to alternate. Okay. G Ahmed, you have a question? या पहले का ये? Okay. Right. So let's try to compute the Fourier transform. And these two cases, I mean, the reason why I particularly highlight this here is because when we compute the Fourier transform, we're going to try to build a connection of what happens when A is positive and what happens when A is negative, right? Achari. So x of e raised to power j omega, let's just apply the definition. The definition is, this is summation n equals minus infinity to plus infinity x of n e raised to power minus j omega n, right? So that's the definition of the Fourier transform. And this is minus infinity to plus infinity. Let me plug in what the signal is. This is a raised to power n u of n times e raised to power minus j omega n. And because of the u of n, the summation now goes from 0 to infinity. And this becomes a raised to power n e raised to power minus j omega n. How do I solve this summation? How do I solve this summation? Is this a geometric series? Can I manipulate this somehow so that this becomes a geometric series? Anyone? Can I write this as something whole raised to power n? That's a geometric series, right? So can I write this something as whole raised to power n? I mean, given this, you should be able to do this, right? So is this something whole raised to power n?
Sir, a raised to power minus 1 over j omega into e raised to power minus j omega और फिर बाहर n आ जाएगा.
Right, but लेकिन अब्दुल्ला a raised to power e raised to power j omega क्यों आया?
सर एक दफा से मल्टीप्लाई करके एक दफा से डिवाइड करके कर
Right,
देंगे.
but you see, I mean, this is, things are very simple, right? So this is this. I mean, when you're raising something to an integer, okay, yeah, product to an integer. So that's or so what I've used is a fact, simple rule ke a dot b raised to power n is a raised to power n times b raised to power n, right? Product is what is associative, right? So this is a times e raised to power minus j omega raised to power n, right? And then what is this equal to? What is this equal to then? So this is nothing but an infinite series. This is equal to 1 upon 1 minus a e raised to power minus j omega. And remember this, there's a note here, which is that the series actually converge, or the sum converges. Why does it converge?
You mean negative? Negative.
No, a is not necessarily negative, right? A could be positive.
Hey, minus jw, minus jw.
Minus jw for what if omega is negative? So then e raised to power j omega becomes positive. Right? So this is another confusion.
So we are increasing n ना तो n increase करने तो वो कहते हैं 0 1 over infinity equals I think 0 to return.
Right. So let me point out a very common mistake that people do, which is e raised to power j omega n is neither an increasing exponential nor a decreasing exponential. It's a complex exponential. It continuously rotates. It's a cosine and a sine. It's just like e raised to power j omega t is neither increasing or decreasing. It just constantly rotates. So e raised to power j omega n also constantly rotates. It does not increase or decrease monotonically.
Okay.
Okay? It's because of a that something happens, right? It converges because the absolute value of a e raised to power minus j omega, which is
less than 1,
equal to absolute of a, which is less than 1. तब सिर्फ कन्वर्ज करता है, वरना चीज कन्वर्ज नहीं करती. And this is something we did in the background 2 lectures ago or 3 lectures ago, right? So when we did that background, when does the series converge? When does it not converge? I mean, when does r raised to power n going from 0 to infinity is equal to 1 upon 1 minus r? And this is true only when the absolute value of r is less than 1. Otherwise, it does not converge. Right? So that's a fact that we use. That's why the absolute value of a has to be less than 1. If the absolute value of a is greater than 1, this series does not converge and the Fourier transform does not exist. Okay? All right. So x of e raised by j omega, we found out, is equal to 1 upon 1 minus a e raised by minus j omega. Now, let's try to compute the absolute value of x of e raised by j omega. The absolute value क्या होगी? The absolute value is just equal to the 1 upon 1 minus a e raised to power minus j omega, right? Multiplied by the conjugate, 1 upon 1 minus a e raised to power minus j omega, the conjugate of this, and raised to power half. Right? That's how we compute the absolute value, right? And this becomes 1 upon 1 minus a e raised to power minus j omega times 1 minus a e raised to power plus j omega. Conjugation, that's all that happens. The phase is reversed, raised to power half, right? And you do the product, what you get is 1 upon 1 minus a e raised to power minus j omega minus a e raised to power plus j omega and plus a squared raised to power half. And I can simplify this a bit further as well. This is 1 upon 1 minus 2a cosine omega plus a squared. Abdullah, you have a question?
So can you help me imagine that how does x of e raised to power j omega converge? Because we said that after 2 pi that DTFT is periodic. तो ये भी periodic नहीं होना चाहिए, तो periodic signal कैसे converge कर सकता है?
नहीं, so देखें periodic signal frequency में periodic है.
Yes sir, तो वो frequencies के
और converge करने का क्या मतलब है? Converge करने का ये मतलब नहीं है कि वो कहीं जाके die down कर जाता है. When I say x of e raised by j omega converges, that does not mean that x of e raised by j omega goes to 0 as omega keeps on increasing. That's not what it means. When I say
it means that it goes to certain value.
That means कि उसकी value हमेशा infinity से कम रहती है.
Oh, okay.
ठीक है? That's what convergence means. Right? It never goes up to infinity.
Okay.
समझ आई? ये थोड़ा और गौर करना है.
So I'll think about it more.
All right. Okay, so the convergence is the amplitude never goes to infinity. That's what I meant by convergence. No matter what omega is. Okay. Achari. So this is the magnitude. Now, if I plot this magnitude up, right? So if I sketch this, या चलें ऐसा करते हैं कि मैं ये कहता हूँ कि यार just for the sketch, just for the sketching, what I want to do is, okay, let me try to compute the magnitude of x raised by j omega at omega equals 0. Right, let me rephrase this slightly differently and say this is 0. What is this equal to? This equals to 1 upon 1 minus 2a plus a squared and half, and so this becomes equal to 1 upon 1 minus a. Okay, and let me look at the other extreme, which is what is x of e raised by j pi. What does the absolute value look like at frequency of pi radians per sample. This is 1 plus 2a plus a squared raised to power half, and this is 1 upon 1 plus a. Okay. Abdullah, question abhi bhi hai? Ahmed, aapka, do you have a question? Okay. So this is omega. And what we want to do is we want to plot x of e raised by j omega, or the absolute value for that. Let's consider first of all the case when a is greater than 0, or 0 is less than a is less than 1, right? So let's consider a positive value of a. If a is positive, then 1 upon 1 minus a is actually greater than 1 upon 1 plus a, right? So if this is 1 upon 1 minus a, at a frequency of pi, you're going to have some value which is 1 upon 1 plus a, which is going to be smaller, right? And if you sketch this out, what it looks like is the following, right? Something like this. There's a cosine there as well. Take it to something like this. And it 2 pi pe jaake goes back. And you can actually verify that this periodically extends. I mean, the function that you have is periodic. Baki se aage piche, I mean, the similar thing is going to go. Now, so this is for the case when a is positive. What about the case when a is negative? What happens there? This is omega. And what I want to do is I want to plot the case when minus 1 is less than a is less than 0. And this is x of e raised by j omega. And in this case, you'll find out kg at omega equals 0. This is, once again, the signal is 1 upon 1 minus a. But since a is negative, 1 upon 1 minus a is actually smaller than 1 upon 1 plus a. And if this is pi, and this is 2 pi, this is what the Fourier transform, or the amplitude or the magnitude of the Fourier transform looks like. Right? So in this particular case, so yeah, this is pi, right? When a is negative, I see that there's a peak at pi, at the frequency of pi, and when a is positive, the peak is at omega equals 0 or omega equals 2 pi, right? Can you make sense of it? So in other words, what I can say is, okay, when a is negative, there are more high frequency components in the time domain signal compared to the case when a was positive, right? Remember, when a is the frequency of pi is the highest frequency, and this is the high frequency regime, right? So this is the high frequency regime. So when a is negative, the high frequencies are more compared to the low frequencies, and when a is positive, the high frequencies are lower compared to the low frequencies. Okay, the contributions are lower, right? Does that make sense? Does that make sense? If you just look at the time domain signals for both cases, when a is positive and when a is negative, right? So here's what it is, right? And you can clearly see that when a is negative, there's a lot more variation in the signal because it goes up and then suddenly goes down, and then goes up and suddenly goes down, right? So there's a lot more variation, or the rate of change is a lot higher for the case when a is negative compared to the case when a is positive. When a is positive, it's a relatively smoother signal compared to the case when a is negative, right? And that reflects in these Fourier transform for these two cases, right? For when a is positive and a is negative. Okay? So everything just sort of clicks together, right? Abdullah, what do you want to say? Reflection against mid value?
सर उसकी सिग्नल की एवरेज वैल्यू पे अगर हम लाइन ड्रॉ करें तो उसके अगेंस्ट रिफ्लेक्ट हो रहा था वो
Against reflect हो रहा था. Okay, so actually you can actually show that's actually a shifted version.
Oh yes, इस तरह कर सकते
इस तरह देखें ना तो this is something you can show. When we do the properties, you will be able to find out कि ये ऊपर वाला सिग्नल उस निचले वाले सिग्नल का सिर्फ एक shifted version है,
yes
right? And that's something we can try to figure out when we do the properties as well, the multiplication properties, right? Let me do another example. And the reason why I'm doing these examples is not only because I want to make sense of what Fourier transform is and what uske kya implications and so on and so forth, but also to go through these this rigor of evaluation or computations or discrete time mein. People are more familiar, I believe, with the integrals, right, or with calculus. Like in this discrete sums are perhaps things that people have not seen too much. Okay, right. So the second case is the following: x of n is now a raised to power absolute of n, and I know that absolute value of a is less than 1 once again, right? And I am required to compute the discrete time Fourier transform for this particular signal. And once again, I plug in the definition x of e raised to power j omega, right? And this is summation n equals minus infinity to plus infinity a raised to power absolute of n e raised to power minus j omega n. So by the way, what would this signal look like? I mean, if I were to sketch this out, किस तरह का होगा? Symmetric about y-axis.
Symmetrical, sort of like rotation.
Excellent.
It will be certain positive.
Yeah, it would decay on both sides if a is positive, and if a is negative, तो फिर क्या होगा?
It would still decay.
It would still decay, लेकिन what would be different?
Still decay.
So x पे negative में चला जाएगा instead of being.
Right. So it would keep on alternating, right? Even or odd values.
Yeah.
Even values are positive and odd values be negative, and so on and so forth. Right? Just like the case we had up above. Right? Right. So let's do this evaluation. Talha, how do I do this evaluation? क्या करूं मैं?
So इसको a को इसको piecewise करें a को since a has jet modulus.
Yeah. So
we make two separate इसके दो cases बना रहे हैं जिसमें a is greater than n is actually
right.
greater than 0 and n is less than 0. So
right.
n is minus infinity to 0.
Right. I need to break it up into two intervals, as you said. Right?
Yeah.
The first is when n is negative, right? And the reason why I do that is because the behavior of the absolute value is different when n is positive and is different when n is negative. Okay. This is a absolute n. It is minus j omega n. One thing I do want to point out is
absolute हम खत्म करते हैं.
Absolute value भी खत्म करता हूँ मैं, बिल्कुल करता हूँ, right? But I'm gonna do it stepwise. One thing I do want to point out is
Sir, question. Imagine when it's 0 or 1 to infinity क्यों जा रहा है?
Yeah, that's what I was pointing out, KG. This should not go from 0 to infinity.
Why?
Can you write my answer? Or somebody else?
I said why?
Yes. Jitala, go ahead.
So there is a discontinuity. That's why we are not using an integral. This is a summation.
This is a summation. This is not an integral, right? So if you had n equals 0 here as well, so this would have been counting n equals 0 twice. Right? दो terms होती हैं
ठीक है.
एक पहले summation में एक दूसरे summation में, but in the original summation you just have one value for n equals 0, right? So you cannot have n equals 0 here as well. It has to be n equals 1, and this is a very common mistake the students do, right? Or many of us do, right? Now what I do is, as Talha suggested, is to get rid of the integrals. But when n is negative, so what happens to the absolute value? So get rid of the absolute value, sorry. When n is negative, what happens to the absolute value? What is absolute
It
value?
becomes positive.
It becomes positive, Tuni.
Negative.
This is minus n.
Listen, ठीक है समझ आ गई.
And when n is positive, all values of n which are positive, it stays as n. Okay, n e to the minus j omega n. Right? And then I can go about more or less the same methodology, a times e to the minus j omega, and then this is raised to power n, plus this is n equals 1 to infinity. This is a e raised to power minus j omega. Sorry, 1 minute. This is e raised to minus 1. So this is minus n, right? And this is e raised to minus j omega raised to power n. Okay, go. Okay, that's okay, Tala. So what do I do here? Right? I can make a change of variables, right? I can change of variables. What are those? The first is m equals minus n. That's going to be the first summation. And in the second summation, I'm going to use, let's say, s equals n minus 1. And the reason why I'm doing this s equals n minus 1 is so that when n equals 1, s becomes equal to 0, and the summation transforms into something that we're familiar with, in the infinite sum that we're familiar with, right? That is the standard form for that, right? And therefore, this x of e raised by j omega becomes equal to summation. This is m equals 0 to infinity. This is a e raised to power j omega raised to power m plus, and this summation, this is s going from 0 to infinity. This is a e raised to power minus j omega, and n is equal to s plus 1, right? And now things are going to become easy, right? So this becomes equal to 1 upon 1 minus a e raised to power minus j omega plus j omega, and plus this is a times e raised to power minus j omega times 1 upon 1 minus a e raised to power minus j omega. Okay, and I can simplify this further, right? If I multiply the denominators, I'm gonna get 1 minus 2a cosine omega plus a squared. I'm writing this out directly because this is exactly the calculation that we did up above in the example 1. Okay, this is 1 minus a e raised to power minus j omega plus a e raised to power minus j omega minus a squared. Okay, and what happens here? Then this cancels, right? So this cancels, and this is 1 minus a squared upon 1 minus 2a cosine omega plus a squared. Let me see. So again. Yep. Yeah, that's it. Right, which is you see is real, and actually is even as well, as you can verify. Okay, and if I were to sketch this out, and I'll just quickly sketch this without going through why you get the kind of curves that you're getting. So for those two cases, so this is the case x of e raised by j omega when 0 is less than a is less than 1. And this is the case when -1 is less than a is less than 0. And the curves that you get are something like this. This is 0, this is pi, and this is 2 pi. And as opposed to here, this, you get the same sort of curve, except k with a peak is going to be at pi. And so on and so forth, right? And this is minus pi. Okay, and once again, we get the same idea that when a is negative, there are more high frequency components compared to when a is positive, and that would make sense because the signal is much smoother for positive a. Okay. Any questions about this example before I do the next one? Okay, so here's the third example.
Could you say the pi, minus pi to pi से लगाते हैं, boundary मतलब के?
Yeah, so you could use minus pi to pi or from 0 to 2 pi.
Same ही लगता है.
Same ही लगता है because it's periodic, right? I mean, we have not explicitly talked about the periodicity, but it's clear from, I mean, if you just look at this expression here, I mean, there's an inherent periodicity because of omega. Right? The cosine omega, that's periodic.
So जब हम continuous integration minus infinity to infinity तो वो उसको replace करेंगे हम 0 से 2 pi या फिर minus pi से pi.
Yeah, and that's enough.
ठीक है.
That's enough to depict. Yeah, because of periodicity.
लेकिन जैसे continuous time थी ना तो discrete time के लिए क्या होगा फिर?
Any continuous time, it has to be from minus infinity to plus infinity. Discrete timing, you can take it from 0 to 2 pi or from minus pi to pi.
जैसे फिर उसके फिर आपने density आपने लिया था u from u into t minus 1 plus u of t plus 1. तो फिर उसको क्या होगा? उससे क्या कहते हैं? उससे integrate कहाँ करना होगा? सिर्फ -1 से 1 तक?
Yeah, but that's continuous time, right? We're talking about discrete time now.
Okay.
Right?
Discrete
So,
time.
And discrete time, I think what u of n minus 1, you have to let me, it's a related example here, right? Which is x of n is equal to 1 for all values of absolute value of n is less than capital N and 0 otherwise.
हमने n से minus n तक करना होगा summation.
Exactly, right? So, and if you were to write this as a unit step, so this is u of n plus capital N minus u of क्या होगा?
n minus u of n minus n plus 1.
अगर मैं ये लिख दूँ,
इधर तो वैसे क्योंकि आपको 2 बार n आ रहे हैं, से 2 बार क्योंकि से तो बीच में आपका 0 भी आपको कन्वर्ट मतलब कि 0 भी आ रहा है, 0 2 बार आ रहा है, 0.
good, right? So I want others to take a look and tell me, okay, is this correct or not? Anybody? Is this correct or not?
So n plus 1 होगा.
Right? Why? I can quickly take a look, right? So how? Right? So if this is minus n, right? This is u of n plus n, right? So u of n plus n, right? और u of n minus n कहाँ से start होता है? वो n से start होता है. If this was, for example, plus n, it started from here. When I subtract the pink from the blue, right? So I'm gonna get a flat signal which appears all the way up over here. ये वाली जो value है plus n वाली, that's going to be cancelled out, right? So essentially मुझे यहाँ से start होना चाहिए था, right? So this should have been n plus 1. So this should have been minus 1 here. You get it? Right. But nevertheless, I mean, that was not the point. I mean, asal point kya tha? Asal point tha to compute the Fourier transform. How do you compute the Fourier transform? In order to compute the Fourier transform, I just apply the definition, right? Definition is what? N equals minus infinity to plus infinity x of n e raised to power minus j omega n. And this reduces to what? This reduces to n going from minus capital N to plus capital N e raised to minus j omega n. Okay. Now, can somebody help me out here? I mean, how do I solve this summation? And it's not an infinite summation anymore. This is a finite summation, right?
उनको ऐड करने से हर एक पे वैल्यू जो भी है
Add करने क्या होगा?
2n plus 1 2n plus 2n
Okay.
something like that.
But
2n into e to the power minus tw1.
But how do I translate this into a form that I'm familiar with?
Cos और sin में कन्वर्ट करते हैं.
Time में convert करते हैं.
दो समेशंस नहीं
सर
Okay. So one somebody says कि जी दो summations हो सकती हैं. That's actually correct. You can have two summations here, but that would involve more steps. There's one way to do it. जिसमें एक step में एक तीर से दो शिकार. यानी you don't need to.
multiply with 2n.
Right. So now what I'm saying is, can I make one change of variables here so that this summation that you have here translates or transforms into a form that we're very, very familiar with, right? Which can n equals minus n से start हो रही है summation. Minus n से बढ़ती है capital N तक जाती है. What I want is to have some sort of a transformation so that instead of starting from minus n, this new variable should start from 0.
n plus 1.
I can use a change of variables.
Yes, change of variables. K is equal to minus n.
And then let me say m equals, अब बताएं मुझे.
Minus n. नहीं.
Should be a shifting, right?
Yes.
You know, Abdullah?
n minus capital N. N minus capital N. N minus capital N.
If I do,
N minus capital N.
right, is this okay? Is this good? Anybody else? Right, Hamza, you're there. It should go from 0 to 2n plus 1, right? That's correct. Lekin, what I want you to answer is the thing that you see on the screen, small m equals small n minus capital N. Is that thing gonna work in changing the limits from 0 to 2n plus 1 as you suggest? Right, I can plug in. Ji Hamza, go ahead.
should be plus n.
n small n plus capital N ही होना चाहिए.
बिल्कुल, excellent, right? N plus capital होना चाहिए, right? So that once I plug in small n equals minus capital N plus capital N should be 0, right? That's what I wanted to in the first place, right? So this is a change of variables I'm going to employ, right? And with this change of variables, what I then get is this summation goes from, right, so m equals 0, or when this is capital N, this is capital N, so this is 2 capital N, right? So this is 2 times capital N, right? And I have e raised to power minus j omega and raised to power n, right? So n is small m minus capital N, right? Because of this, what changes is the following. So this is summation m equals 0 to 2n e raised to power minus j omega raised to power m times e raised to power j omega capital N, right? This e raised by j times capital N can come outside of the summation because that's not a function of the variable that we're summing over, right? And this summation is from m equals 0 to 2n, and I have e raised to power minus j omega small m here, which is now the standard form that we're familiar with. So this is e raised by j omega times capital N times 1 upon 1 minus e raised to power minus j omega. Actually 1 here. And this is 1 minus e raised to power minus j omega 2n plus 1. Okay. Now you can leave this if you want in this form. Like, and it turns out, Kitty, there's a much more, there's a simplification that you could do here, right? And I'm going to go through that simplification to bring this into a nice form, which is actually real. It turns out that this entire thing that you see here is real. It's not complex, right? And yes, you can multiply two complex numbers and get a real number. You can add two complex numbers and to get a real number and so on and so forth, right? The way I'm going to go about this is use a trick. This is e raised by j omega n. I am going to do this. I'm going to say, yeah, let me bring this out as a common factor in the numerator, and this is e raised by plus j omega 2n plus 1 divided by 2 minus e raised by minus j omega 2n plus 1 divided by 2. And in the denominator, I am also going to pick out e raised by minus j omega by 2 as a common factor. So this is e raised by plus j omega by 2 minus e raised by minus j omega by 2, right? And it turns out this entire thing that you have outside, this is actually equal to 1. Everything cancels, right? What do you have here?
Two cosines.
Two cosines or sines?
Cosines, I guess.
Right, so cosine mein there's always a plus here. Cosines mein there's a plus here, right? But you have a minus here, right? So this is actually 2j times sine of whatever this is. Right, so this is 2 times j times sine omega 2n plus 1 divided by 2. And what you have in the numerator, the denominator, that's once again is 2j. But this is sine omega by 2. And this cancels as well, right? And because of this, we get this very nice form. X of e raised by j omega is actually sine omega, and this is n plus half divided by sine omega by 2, right? This is a sinc pulse, or is also sometimes called the periodic sinc, right? And this is similar to a sinc pulse that we have. So say, Kiji, कंटिन्यूस टाइम में हम जो है अगर एक रेक्टेंगुलर पल्स लेते थे उसका फोरियर ट्रांसफॉर्म was actually a sync pulse, right? And over here something similar happens, except that this is a periodic sync extension, right? यहाँ पे this in the denominator you have sine omega by 2. Over there you had an omega, right? So that's one of the differences, right? And if you plot this out, so let's do that. We have 4 minutes, so let me spend time here. Let's say n was equal to 2, right? And I want to sketch out x of e raised by j omega. X of e raised by j omega is real, as you can see, right? So this is omega. And this is x of e raised by j omega. Right, so it has a sync pulse, okay? It looks something like this, right? Which decays as time goes on, or as the frequency goes on, but not monotonically. And goes up again because of the periodicity. And if n equals 2, this first zero crossing is going to be at 2 pi by 5. This crossing is going to be at 4 pi by 5. And this is where pi is. And this zero crossing here is at 6 pi by 5, and so on and so forth. And you can figure out, Kitty, why is this so, right? Because sine pi is 0, sine 2 pi is 0, sine 3 pi is 0. That's what you would do, as we did in the continuous time, right? And this is a periodic sync, right? What about this height here at omega equals 0? वो किस तरह निकालें? So what is
L'Hopital?
Okay?
बस वही बस वही डालेंगे सर e power j0
Right.
और फिर sin of 0 आएगा, sin of 0 is equal to 1 over 1 to 1.
Sine 0 is 0, right? So that's 0.0.
0.0. So undetermined.
It's not undetermined. You could use L'Hopital's if you wish, but other than that, you can just go back and see here, what is x of e raised by j0? X of e raised by j0, if I go back here, omega equals 0 यहाँ पे put करें तो फिर क्या होता है?
1.
Yeah, so that's 1, right? So x of e raised by j0, x of e raised by j0 is actually summation n equals minus infinity to plus infinity x of n, right? It's just the DC value or the area under the curve, if you will. I mean, the discrete time version of it, right? And this is equal to, therefore, summation from minus n to plus n, summation of what? Summation of 1. And this is equal to, how many values do you have here? So you're adding 1 how many number of times?
2n plus 1.
2n plus 1. Right? So this height here is 2n plus 1. This is 2n plus 1. Right? So let's just, keep this in mind. Okay, the Fourier transform of this pulse, right? The rectangular pulse in the discrete time domain from minus n to plus n looks something like this, which is a sync pulse. Okay? And this has high frequency components, but those high frequency components are relatively low compared to the low frequency components. Low frequency components ज़्यादा हैं, high frequency components कम हैं, right? And these are going to play a part when we talk about filters, okay? High pass filtering and low pass filtering. Okay, so I'm going to stop here. If there are any questions, I can answer those. I will write down some exercises for you to think about. And then, so I'll put this up on the notes.